Yes. Welcome, everyone. I'm Lori Brown, president of the GPE section, and today it's my great honor to introduce our 2018 Bullard lecturer, Dr. Lisa Talks. Lisa is a distinguished professor at the University of California, San Diego. I'll get it out correctly. And also a senior scientist at Scripps Institute of Oceanography. She received her undergraduate degree from Yale and her graduate degrees from Columbia University. She's the author of over 200 publications. She's familiar to all of us as a very creative and a very formidable scientist. Her research touches on all aspects of paleomagnetism, rock magnetism, and beyond. To set the stage, Lisa's first publication, written when she was a young graduate student, was a single author letter in Nature in which she used magnetostratigraphy in Pakistan to date the age of an ancient ape. Fast forward to today. This year, Lisa's been involved in publishing papers about global paleosecular variation, a critique of the day diagram, paleointensity of Holocene lavas, and others. Never one to sit still, she has extended her energies into other projects, including writing and maintaining a free and open textbook, The Essentials of Paleomagnetism. With her colleagues at Scripps, she has envisioned and whipped into shape MAGIC, a database for all of that data we turn out daily. And she's written the PMAG-Pi software so that we all can deal with that amount of data. Her most recent activities have included working with colleagues at the National Academy to produce an impressive report entitled Open Science by Design, Visualizing a Vision for 21st Century Research. Along the way, she's received numerous awards and honors, including fellowship in AGU, GSA, AAAS, and the National Academy. She has served AG well as president of our GPE section, as the general secretary and treasurer for the union, and currently chair of the publications committee. I've known Lisa since she was a graduate student, and what I like best about her is that she pushes and prods us all to be better scientists and better citizens of our changing world. Today, her topic is hunting the magnetic field. Lisa.
Thank you, Lori. So I'll just get right to it. First, I want to thank some people because this is a great honor, and I'm touched that I was considered for this lecture. And so I want to thank some people that have been very important to me. First of all, my parents, without whom all this would not have been necessary. And my two advisors, Dennis Kent and Neil Updike, who, despite all evidence to the contrary, saw something in me and let me do my thing, and also taught me everything I know about science, or tried to teach me how to do science. And I'm deeply grateful to these two men. Thank you, Dennis. And Neil's here in spirit, I'm sure. And my husband, Hubert Staudigal, who has stuck with me thick and thin, and we're in it for the long haul. And I love him very much. And my two kids and their wives. And my little grandbaby over there on the left, I just can't stand it. He's the best new thing in the world. And so I'm deeply grateful to my children for allowing me to do science while being their mom. and all my friends, co-authors, colleagues, and the committee that selected me for this honor. Thank you very much, Lori and Catherine. And I can't name everybody because, as she said, I wrote too many papers on too many different subjects. So, back to the talk. What I want to talk about today is something that's been on my mind and keeping me up at night, and that is how to study the ancient magnetic field through what are non-ideally designed materials left magnetic by some process which is not always well defined. So why study the magnetic field? There's things we might want to know. Some people, I mean, a lot of people know more about these questions than I do, but they strike me as interesting questions. So where does the field come from? I think we know that, right? It's from the inner core or the outer core roiling away. How long has it existed? This is still a matter of debate. As you go back in time, it gets harder and harder to figure that out. And there's often the question, did it play some role in allowing life on Earth? I don't know. I talked to a space physicist on Sunday, and he said, nah. So I said, well, why do we always say that? But other interesting things, I mean, what's its average strength? Is it today's field strength, or is it much less than that, half of that? Over time, how fast, how much does it vary? How fast can it change? I've gotten into trouble recently by saying it can change really fast, at least locally. And what can it tell us about processes deep in the Earth? I guess most people would agree it has something to do with the deep interior of the Earth. And so by studying the Earth's magnetic field, perhaps we can provide constraints on that. So how do we study the magnetic field? Well, there's direct observations, satellites, ground-based observatories, other human measurements, captain's logs. I see Jeremy Bloxham in the audience, and that's what he did. You can use big computers, bigger than we have. We can use the biggest computers we can get our hands on to do numerical simulations, like following along the lines of the classic paper, the Glassmeyer and Roberts paper. There you see the famous figure that I've already seen, I don't know, 16 or 20 times, and it's only day 2 of AGU, where you simulate the magnetic field. Of course, those are not really like the Earth, are they? But they may have aspects that are like the Earth. You can also, if you're brave enough, you can make dynamos in the lab, or you can try. They're a great, I wish them success. Working with liquid sodium is kind of scary, I think. But what I do is I study what I call incidental or accidental, indirect measurements of records of the Earth's magnetic field that are in geological and archaeological archives. So that's what I'm going to talk about today. Accidental records include sediments. They get magnetized, tiny particles become aligned with the magnetic field, sort of, and they get fixed in the sedimentary column. This is all a mystery how it actually happens. It's very difficult. There's no theory for it. And so I've decided to go to things that I thought had a theory, which were igneous rocks, because we have Néel theory, which applies to things that were heated and cooled from high temperature. So igneous rocks and archaeological artifacts get magnetized when they cool, and in the presence of the field, and they do preserve some record of the Earth's magnetic field. So that's what I'm going to talk about. So what happens is igneous rocks, lava, for example, or a pot. Lava is extruded very hot above, and it's completely non-magnetic. And as it cools, certain minerals become magnets, and they come into equilibrium with an applied field. And when they cool down further, that equilibrium magnetization gets frozen in, and you have a record of it's called blocking. You have a record of the geomagnetic field, and this is known as a thermal remnant magnetization, TRM. So here's the expanded version of that. The Nail theory from 1949, 1955, pick a paper. One's in French and one's in English, but you imagine a population of magnets that have two possible directions, because the in-between directions are at a higher energy, and so left to their own devices, they'll be either aligned in this way or this way. And they can jump from one to the other, but they have to go over this energy barrier, delta E. And if you apply a field at some angle to this, you end up with a preferential, this is at a very slightly lower energy than this, and so you end up with more magnetic moments in this direction than in this direction, and this leads to the Nail equation. Well, there's a Boltzmann distribution, so that the ratio of things in the positive direction to things in the negative direction, there's an exponential function of delta E, our friend up here, and Boltzmann's constant K, and the temperature at which equilibrium is maintained. So I'm going to call this the blocking temperature. So at high temperature, as you're coming down, it maintains equilibrium, and Nail realized that there's a very sharp temperature at which things go from maintaining equilibrium and flipping back and forth between these two directions, and they're frozen. So the time constant at which this flipping occurs is billions of years, so that we preserve this record of this equilibrium magnetization. And this boils down to, with little mathy bits, which aren't actually in Nail, but you can work it out. The magnetization which you acquire, the thermal remnant magnetization, is proportional to the applied field. And it has this hyperbolic tangent function relationship where delta E is this energy here, and KT. So it's a function of temperature, and the energy, this anisotropy energy, is called delta E. This hyperbolic tangent function for small fields is pretty linear. It looks like a line. It acts like a line. For larger fields, then it, of course, saturates out to some saturation magnetization. But for most Earth fields, although not all, some of our experiments are nonlinear. But we can measure that, and we can correct for that. And if you measure the magnetization that you get of this rock or pot here, and then you give it thermal remnants in the lab, and measure the magnetization, you can determine the slope. If you assume it's linear, then all you have to do is multiply the ratio of the remnants that you measured to the original remnants to the remnants given in the lab by the lab field, and you get the ancient field. Bob's your uncle. Boy, that's easy. So that's the basis for the paleointensity experiment. It's a lovely theory. The problem is that the function's not linear, and many specimens, if you heat them up, they change. Things cook in the lab, and you change the magnetic properties of the rocks, and you're dealing with a different slope than the original slope. And the lab TRM may have been acquired more slowly or more quickly, most often more quickly than the original, and that slope is rate dependent. There's also, if those magnetic particles are not uniformly distributed in orientation in the rock, you'll have an anisotropy, which needs to be measured and accounted for. And rocks, unfortunately, don't just sit there. They get hit by lightning, they get remagnetized, they change, they acquire magnetization in the field, and so the NRM, the natural remnants, may be multi-component, and so it becomes more complicated. Which one's the original one? How can we tell? How do you know whether it remained reliable? So there's a number of assumptions built in to this experiment, and one critical one is that if this laboratory remnants, if it's acquired, let's say, by cooling from 400 degrees centigrade, that you can completely erase it by reheating it to 400 degrees centigrade and cooling it in zero field. So there's a reciprocity requirement, and there's some other assumptions that I just went over. So sometimes these are not met. So in order to, a good experiment will build in tests of the assumptions. So did the rock alter? Is the lab field parallel? Is the lab remnants parallel to the lab field? Is this a linear relationship of the remnants to the natural remnants to the induced remnants? And so instead of just giving it this total TRM, many of us who follow the Tellier-Coe-Aitken school of thought will creep up on the magnetization gradually, heat it to, say, 100 degrees C, and then measure the remnants, and then heat it up to 100 degrees C, and then measure it, cool it in a field, measure the remnants acquired, and then you can watch the natural remnants decay down like this and watch the induced remnants be acquired. You can monitor the direction of your cooling steps as you go. The natural remnants should decay to the origin, and then you can plot the natural remnants against the induced remnants, and if it's a nice straight line like this, everybody's happy, except when it fails for some other reason. And you can, at each temperature step, you could go back to an earlier temperature and repeat it to see if the capacity to acquire thermal remnants has changed. So this is the basic plot, the ARI plots that we use to get, and the slope of that line multiplied by the lab field is the ancient field that we infer from this specimen. So these experiments have been done, similar experiments have been done since Königsberger invented this method in 1936, and then followed shortly by Tellier. Königsberger was working on rocks, and Tellier was working on archaeological artifacts, and his data look a lot better. So let's take a look at the database that's accumulated over the last I can't even count that high, since 1936. And all the data that we can get are housed in a variety of databases. One of them is Andy Biggin's The Pint database. Most of those data are also in the MAGIC database. The difference between the two is the MAGIC database includes all the measurement data, so we can reanalyze the data if we get a bright idea about what would be a better way of assessing the data. So if we look at the data over time here, most of them, you can see that this is plotted as what's called virtual axial dipole moments. So it's the moment of a little dipole at the center of the Earth that would have given rise to the intensity observed at the location. So it takes out the latitudinal effect. And The long-term median value is about, believe it or not, it's 42, and zeta amp-meter squared, and the present field is about twice that. And so, but there's an awful lot of scatter. So is the field just rapidly varying, or is this real, or what? And we argue endlessly. Can you see the beginning of the inner core in there? And Peter Driscoll will say, yeah, there it is in that gap right there. Way. So ideally, we have experiments that would test the basics of the method. Most of the data in the database we don't have the original data, so we can't do any kind of looking at the data. And most of the data don't meet the test. Because of that, we can't test the basic assumptions in the method. So I'm just going to look at some data with you, walk you through my thought process recently. We have this idea that, on average, the field is equivalent to something created by a bar magnet at the center of the Earth, the Dipole Hypothesis, to first order. And it makes specific predictions about the directional and intensity behavior as a function of time. So, as a function of latitude, sorry. So we start with the GAD hypothesis, geocentric axial dipole hypothesis of Gilbert, 1600. Thank you, Gilbert. And of course, the real field is much more complicated than that. And you can see an example. This is a 2005 IGRF. And because of the complications, you have deviations in the orientation of the horizontal component of the magnetic field called declination. And inclination is the dip from the horizontal, and that varies as a function of latitude. You can see in the left-hand figure, of course, it's this latitudinal dependence. And so there's these two functions that you get from a dipole hypothesis. One is that the inclination should vary as the function, twice the tangent of the latitude. And the intensity is also predicted to vary by a factor of 2 from the equator to the pole. And using this little function here, so if you know the moment, you could predict the magnetic field intensity as a function of latitude. So we can go compare this to the data. Great, so we've got this IGRF representation. What happens if we just look at that? You go sample around, virtually sample around, evaluate the field directions as a function of position around the globe, and you plot those against the inclination against the latitude, and you get the line. The red line is what you expect from a dipole, and the data, the black, are the data that you see around the globe, and so everything's cool. That's why Gilbert said it was the Earth is a great magnet. And you can go to deep sea sediment cores, which Neil Updike and Henry in '69 did, and just plot averages of inclinations as a function of latitude. And you can see that's pretty good. Of course, there were some arguments. There's a little G20 in there and whatever. But to first order, the dipole hypothesis works pretty well. So we do the same thing for intensity. And you go around to the same spots, and you evaluate the intensity of the field at those places. And you see that the intensity, this red line is that dipole equation. Northern hemisphere is pretty good. The southern hemisphere is a mess. And it's because of this big South Atlantic anomaly. And so what we hope is that this would average out over time, and we'd get this nice dipolar signal so that we can, we would be successful. So Tonica, basically the same idea as what Updike and Henry had. They went to lava flows around the world, and this is the first the paleo intensity database Tanaka, he published this in 1995. He went as a function of latitude. He did the experiment. And you look at that and you go, great, I can see the dipole in there. But of course, there's this huge scatter here. And there's only 5 data points from the southern hemisphere. And so let's just look at the database today. And this is if you take the data for the last 5 million years, so we're not talking about plate motion, you plot the intensities against latitude, and this should give everybody the willies, because there's, I don't know. That's pretty bad. Let's just admit it. So what are we doing? That's the question I ask myself when I wake up in the morning. What are we doing? What are we doing wrong? What could go wrong? In case, this is funny because the helicopter's engine hood is up, and that's never a good sign. So are we comparing data from different field states, different ages? Does the field change really fast? Is there something wrong with a dipole model? Geez, then all polar wonder paths are wrong. So let's not go there. Is there something wrong with the intensity experiment? Is there something wrong with how we're treating the data? You know, what is wrong? I guess you'll all agree that something's wrong. So it gets worse. If you go to one single lava flow and plot all the data that came from that one lava flow, 1960, all the holes were there until last summer when they got covered up by the 2018 lava flow. So don't try to go back there right now. So everybody had this idea, well, we got to ground truth our experiments. So a lot of different people, oh, you know, this is the cast of the greats in paleointensity. And the data from this lava flow range from lower than anything observed on Earth today to higher than anything on Earth today, regardless of latitude or place, and they're all supposed to be the same answer. So something is wrong with how we're doing this. We need ways to eliminate or downweight the bad data and select the good data or enhance, you know, get the right answer out of noise. It's basically what this boils down to. And we also need more experiments that where things are done in known fields, so we can figure out whether we can get that answer correct. So here's some examples. The one on the left is what we'd call good data. It's like the one I showed you before. So nice straight Array plot. One on the right, highly curved. And interestingly, these come from the same lava flow. And if you take even the total TRM, this one, it gives you a completely different answer than this one. And yes, the right answer's in there somewhere, but which one is it? Oh, I don't know. So we're taking a different approach to the data analysis. And Brendan Seish, my grad student, gave a talk on Monday, and he was giving you a preview of what we're working on, trying to figure out how to do this experiment. Does this mean I only have 1 minute left?
No, ignore that.
Okay, because boy, that went fast. So I thank you, Greg Patterson, for collecting a large data set from many different labs, done in many different ways, on specimens whose cooling field was known. So this gives us a test bed where we can play with different ways of interpreting data to see whether we ever get the right answer or not, and what sorts of things give you the right answer. We've added to this, and it's hopefully growing. You know, anybody who's done this experiment, we can put it in the MAGIC database, and then we can all play with the data. So here's an example of one study, which I find very interesting. It was done by Krasa et al. In 2003. All the data are in the MAGIC database. And what he did was take carefully sized materials and give them a TRM in a known field of 60 microtesla. And then he did the Tellier experiment on it. So this one is the 23 nanometer one, and it gave absolutely the right answer, 60 microtesla, boom. It's gorgeous. And then as you get to larger and larger sizes, this curve happens, right? That they become more saggy. And you have, and if you can see the x-intercept, if it intercepts at 1, then you've got the right answer. But if it intersects anywhere else, like over here, if you did a total TRM, you would get this answer, and you would have, if you fit a best fit line, you get 47 microtesla. And if you do a total TRM on this, like we're supposed to be able to do, you get the answer of 42, which is not 60. And so Brendan's approach to this is to take something that's highly curved, or take a data set and try to fit as many straight lines, because the theory from Tellier, from Néel, tells us that it should be a straight line. So our assumption is that there's a straight line in there somewhere. And then he uses a Bayesian approach and fits a bunch of straight lines, which then you can plot in this way. This is the intercept, the y-intercept, and the y-axis is related to the slope of the line, which gives us the field strength. This is the right answer for this one. This is this 12 micron magnetite sample. And so you can, this is the data, the range of data that you could have from this sample if you assumed a straight line fit. And so the answer that he gets is between the 50% credible intervals are between 35 and 62. And the right answer was 60, so yeah, but those are huge uncertainty bounds. But the right answer was in there. And so you do that on all the samples, and you see the straight one, this guy's the straight one, and then you can, this guy's the horrible one I just showed you. And then if you sum these all up with no particular additional criteria, you get this plot where the right answer is this red line, and the peak here is very close to that. These are the 50% credible intervals, and so the answer is something like between 45 and 60, or 55 and 65, which is not too bad given that the data are so horrible. So conclusion one is that curved array plots can give very inaccurate and imprecise answers, while straight ones seem to give the accurate and precise answers, or can do that. If you have data from enough specimens, maybe you can pull out the right answer by downweighting the nonlinear ones. And paleointensity methods that don't test for nonlinearity and have few specimens are likely to give the wrong answer. So what causes this curvature? I was arguing with Wape Wong today. In this case, it's clearly domain walls, because these are very large, large magnetites. That can give you curvature. That's been known for a long time. But these Hawaiian data that I showed you earlier do not they're not large enough to have domain walls. So why are they curved? So this has been bothering me. And the twin question of why they give the wrong answer when compared to straight Ri plots. So I've been working on this project. How much time do I have? Okay, so with a set of data, a set of samples that come from all over the world, and some of them are beautifully behaved, like this upper left one. This is an original one, original TRM, and then some that are highly curved, giving the wrong answer, apparently. And then we gave them a fresh TRM in the lab, and this happens all the time, where the fresh TRM is straight, whereas the original one was curved. Why that happens is a mystery. And so we took a bunch of samples like this, 12 of each type, and then gave some a fresh TRM, and others we set in various orientations with a lab field and let them sit there for 2 years, and then some are still sitting there for 3 years. So then we took the fresh TRMs and tried to do this experiment and got answers. And here, this is the lab field that was given, 70 microtesla. These are the straight ones, and they have a actually very tight median value and very high precision answer, so they do give the right answer. These are the curved ones, or were curved, now they're straight, and they are all over the place. They're just, interestingly, the answer is not biased, but it's very high scatter. So you could get the right answer if you had enough specimens like this. But then, looking at the aging experiment really is fascinating. So this is the set of samples that were straight. So the original sample would be the blue one, and the red one would be a lab TRM of a sister specimen. And basically, when you compare blocking temperatures before and after aging, this is aging 2 years, nothing really happens, and they end up being straight. Straight Ri plots. However, the set that were these curved pathological samples, if you do the same thing and age them over 2 years, the red curves, look, they're all shifted to the right, out to very high blocking temperatures. So these things are starting to curve in the lab over 2 years. Now, from theory, nail theory, Pulaia plots, all that stuff tells you that that can't happen. But it did. And so these guys are becoming more and more curved. And over a very short time scale. So why? What's going on? This is not, and they're not domain walls. They're small. So why does the blocking temperature change? Micromagnetics of Wynne Williams and his team, and Les Nodge, who's around too, can now use very powerful computers to tell us what the actual alignment of spins in crystals would be, and not just assume that they're either one direction or the other. This uniaxial single domain assumption, we don't need to rely on that anymore. So this paper came out, this Nudge et al. 2017 last year, and it blew my mind. First of all, this was known. If you go from tiny crystals, say 60 nanometers or so, you know, they're pretty much below 60 nanometers. They're little cubes. They're pretty uniformly magnetized. As you get larger, the spins start to fan out, and you get this flower. This is from Williams and Dunlop. I think it's is it the 89 paper or maybe a later one? But this was noticed as early as 88 by Chavez and Bertram. And so you get this flower state. It's highly stable. And then we had this thing for larger crystals called a vortex. And you can see that the spins are chasing their tails around, and there's this core on the inside where It's called a single vortex, and these things, what Notch showed is that they're extremely stable. This is the age of the solar system, so this is the time, basically the flipping time between the two stable states. And the age of the universe is great. So these things are way more stable than I would have expected. And the other surprise in this paper was that there's something in between the flower and the vortex, which is just as important and is in all of our samples. And look, here's the blocking temperature. This is the relaxation time, this red thing, and it crashes here. And then it starts to go up again. And so there's something in between the flower and the vortex, which is extremely unstable. And it's this thing, okay, so these guys are wonderful, and these guys are terrific, and we're all happy. These guys, this picture here, I hope you can see it, because it's really beautiful, that Les Notch gave to me. The vortex core is aligned along the magnetocrystalline hard axis. So in that first slide I showed you with the spins in a hard axis, that's supposed to be higher energy. But it's not, and these guys are aligned along the hard axis, trying to go from this state to that state, and they're very unstable, so they're terrible. I call them the bad boys. And the good news is that the flowers are very surprisingly stable, and the easy aligned single vortex material is extremely stable, much more stable than I thought before I read that paper. And, but you have to have samples that avoid this bad boys. I haven't proven it yet, but I think, it's my gut here, which is maybe not so good, but we'll work on it, is that it's the bad boys that are causing the curvature and the aging, because they're in this unstable state. And they're causing all our problems in paleointensity. So where are we going in my lab? So I think there is a way forward here. I'm going to continue to hunt for things that are in the flower state. That's how I've spent my life since the early 90s, is looking for glassy, fine-grained material. The other option would be to look for things that are in the easy-aligned single vortex state, and I believe that, that Tarduno has some of these, and Jeff Gee certainly, and his layered intrusions. These are and they avoid the bad boys. We need to do more micromagnetic modeling, because right now it's, I mean, these are time-consuming models, and we need millions of them. So good luck, Les and Wen, they're working on it. And they're building a micromagnetic database. And then we need to find out which sizes and shapes of crystals are controlling this behavior. So we need a synthetic array plot, which is Hannah Esifa gave a poster today, and that's where she's headed. And so we'll figure out, from a micromagnetic modeling point of view, which is the closest thing we have to a theory, it's physically realistic information, and we'll figure out what causes curvature, what causes tails, what causes the aging. And so that if we know what is causing our problems, we can avoid them. I think we should do a lot more ground truthing. I was talking to Beck, she wanted to do the standards, but we need to share in the intensity standards among labs. And we need to get better at the data interpretation, so we don't have this embarrassing result where data from a single lava flow gives you any answer, you know, on the surface of the Earth and probably the entire solar system, unless you go to Jupiter or something. And so in order to use new ways of looking at data, we need to have the data in a publicly available form, and that's this findable, accessible, interoperable, and reusable acronym FAIR that you've heard all over AGU. I saw it maybe 4 times today. It's AGU's acronym for how we're going to move forward about getting reproducible and believable data. And so I encourage everybody who has the data to put it into, doesn't have to be magic, but it has to be somewhere that we can get at it. Magic is one option. I don't know of any other options right now, and if you want to spend 10 years and $12 million developing your own database, go ahead. And so I think that we do have a way forward, and this is where I'm headed, and I'd love to have a conversation with anybody about it, because I'm sure everybody has a different opinion. Thank you.
I'm sure Lisa will take some questions, and if you have a question, just please be sure to speak up.
No question? Come on, guys.
Okay.
Greg.
So just when you're looking at the sort of Bayesian plots, combining all the different results, at least in that example, the synthetic one, it looked as though it was quite heavily dependent on having one near ideal sample.
Right.
And if that one specimen was removed, how would that affect the credibility intervals? So I guess it would go huge.
It makes them huge, which is what you want, because then you know it's a crap answer, right? If you have uncertainty bounds that you believe, then you can use them. Guess what? That's a really not very good result. Throw them away. Yeah, right. Andy.
Sorry, Lisa, you showed a bunch of examples from David Cross's work.
From what?
From David Cross's work.
Yeah, I showed that one paper, yeah.
The only one that gave the right result was the only one for which Nail theory
Worked.
applies.
Correct.
Right?
Yeah,
Everything else, Nail theory doesn't apply because it's the wrong domain state.
that's right.
You and I agree about this.
Yes.
So what our community needs is, instead of measuring all the wrong stuff, methods that can help us to diagnose the domain state accurately and work on that stuff.
Great idea, Andy. I think you should write a paper about that. Yeah. I think.
So, you know, as a community, we love to ignore theory and just get on and measure whatever is out there. And so you point to the hard axis aligned single vortex state as the bad boys, but the multi-vortex and multi-domain are generally
They're worse.
and they're worse. And we don't have a theory for that stuff.
Nope, not yet.
So it seems to me that there's some priorities for us as a community to understand how those things work better, in addition to what the theory tells us.
Yeah, so just building a new theory based on physics for a change, instead of just making it up. Right. More questions? You can attack me later over a beer.
There's one for you.
Oh, okay. Andy.
Your horrible dipole thing in the last 5 minutes before. It was surprising me because at other time periods, we have managed to pull out the dipole quite nicely applying certain selection criteria.
Yeah, selection criteria.
So, yeah, well, what is it? I mean, you know,
There's too many data from the last 5 million years.
you know, is there something special about that data? You know, is it
Oh, I think there's just a lot of data, and not all of it's, in fact, most of it's pretty bad. So, Ken.
So does this all assume the single component of magnetization? What if you have multiple components?
Yeah. So this was, so far, Brendan is working on single components because we're working on these things that only have one component. And that's a very good question. So we're thinking about ways of approaching, if it's sagged, it's not two components, it's a different thing. So he's treating the sag, but with using Patterson's curvature circle approach. But so if it's two components, it seems to me that you could interpret the first line and then subtract that off and then interpret the second line in a method very similar to what we're doing. But I would suggest that you'd have to have it based on the directional data, so you're not just picking what you want. He's almost done with this, but didn't quite make it by the time today, so maybe by Christmas. No pressure, Brenda. But yeah, we got to think about how to deal with multi-component data, and there's ways. We have ways. Any other questions? Okay.
Wait, just one moment. We have two important things to do, so don't leave quite yet. The first one is we get to present Lisa with a completely frameable declaration that she has presented the Bullard lecture. And so thank you for that. And then two important announcements I would like to make. First, I want to remind you all of the union session tomorrow afternoon at 1:40, on which Lisa and Fabio will have organized on grand challenges in paleo and rock magnetism. And it's over in the convention center, so we have to leave the Marriott here and go through the tunnel over there. It's in the convention center 202A, which is up on the floor where the exhibits are. The second announcement I want to make you all aware of, I hope you know already, that the GPE reception will be beginning in just about half an hour, and it's down in the Grand Hyatt Hotel, which is on 10th Street and H. So if you just go out of the hotel here and go over to 10th Street and go down, you'll get there. And it's down on the second floor in the downstairs in the Constitution A. And if you're a little worried because you saw it was at a ticketed event or you didn't sign up for it, please don't worry about that. Everybody is welcome. Please come. We'll have our sort of business meeting and give out some more awards. Okay, thank you.